Hello, AP Stats. I hope you guys are having an awesome day. Today, our lesson is going to be an introduction into what a sampling distribution is. And so our SWBAT is going to be basically understanding what a sampling distribution is, and then look at what the difference is between a population distribution, distribution of sample data, and the sampling distribution is. We'll also look at a definition called something called an unbiased estimator. And then last but not least, we'll look at what the relationship is between sample size and the variability and precision of one of those unbiased estimators would be. Okay, so I know you already have these definitions on your paper, but I'm going to go through what they actually mean. So we have three different distributions that we will be looking at. One is the population distribution, and that is like the true distribution of the actual thing that we're studying. So parameters that we're looking at is the true p, also known as pi, mu, which is the true mean, sigma, or the true standard deviation, etc. So basically, if you were to actually know the true distribution of the population, which is highly unlikely, right? Because, I don't know, what's the mean height of the people in the United States? Well, nobody actually knows for sure, but we have an estimate of it because we haven't actually taken a true census of every single person's height in the US. We've gotten close to it, right? But we don't actually know for sure. But so that would be the population distribution, is the true distribution and the true mean. Then, sometimes we'll take a sample and we'll create a distribution of that sample. So in the height example again, we might take a height, a sample of 100 people in the US, and we'll look at the mean height, or X bar, right, of that sample, of that particular sample. And so you'll have a different distribution depending on what your sample is. Because if I take a sample of 100 people, I'll get a certain mean height. And then if I take a new sample of 100 people, I'll get a different mean, right? So that's the distribution of the sample. Then last but not least is the sampling distribution. So don't confuse these two things because their names and titles are very, very similar, but they're very different things. So the first one is the distribution of one particular sample, but then the sampling distribution is basically like the distribution of all the means in all of the samples that you could possibly ever take. So again, in our height example, right, say we had, for example, we took one sample. Sorry, my writing sucks on these things. But basically, we take one sample and we get some sort of a distribution with the mean of, let's say 5'7", right? And then we take another sample and we get the mean is going to be 5'8" in that sample, right? It's my new X bar. So basically, you take every single possible sample in the entire world that you could possibly take, and then you take all of those means and you make a distribution of the means, okay, of the sample means. So we're going to look at the actual things that I gave you so you can actually see this as an example. So here we're looking at a true population, just like the example we did in class, with 100 red chips, 100 blue chips, right? And we know for a fact that the true population has 100 blue chips and 100 red chips. Why? Because I counted them out for you, because, I love you and I want you to see this in action. Okay, so basically, right, the population distribution is the first thing on the left, right? Because there are truly 100 blue chips and 100 red chips. So that is the true population. And so our parameter P, or pi, is 0.5, right? If we're looking at, let's say, we're going to study a particular parameter, P, is the proportion of red chips. Okay. All right, so this first thing here, remember, we're just looking at the proportion of red chips, because you could find the proportion of blue chips just doing 1 minus or 200 minus whatever we get for the red. So anyways, the population distribution is this first thing on the left here. Again, I apologize for the horrible handwriting. Okay, so that's our population distribution. Okay, so then from that population, we might take a random sample of 20 chips, for example. Okay, so pretending that we never actually knew what the population distribution was, right? Because often we don't actually know the true population. Let's say we take lots of samples of size 20. So we take one simple random sample of size 20, and we happen to get 12 blues and 8 reds. Okay, so if we're looking at P, or P hat in this case now, because we're looking at statistics, the proportion of red chips that we get for this particular sample is 8 out of 20, right? So then, I use my calculator and I say, oh, that's 0.4, okay? So then I have one sample and one proportion of reds, okay? Then I take another simple random sample of 20, okay? So that's when I go down here, simple random sample, another one of 20, and in this particular sample, I get 9 blues and 13 reds. So my new P hat is 13 out of 20. Did I look at that wrong? Yep, that's not 13. That's 11. Don't mind my math. Okay, 11 out of 20, which ends up being about 55%. Okay, so in our second sample, we got 55%. We do this again and again and again and again and again, hence the ... And we repeat this with every single possible sample of size 20 that I could possibly make, which is a huge number of samples. But if we were to do this an infinite number of times, right, and then we took all of those P hats, so 0.4, 0.55, the next one we got 13 out of 20, which is 0.65, right, and we then plotted all of our P hats on a dot plot and made a distribution, we would get the sampling distribution of P hat. Okay. The really exciting part is that for certain statistics, okay, you'll see that after you create the sampling distribution, right, what is the mean of the sampling distribution? Oh, look at that, it's 0.5. And what is the true value of P? Oh yeah, it's 0.5, right? 100 out of 20, or 100 out of 200, right? So that's what's really cool, is that if we can actually look at the sampling distribution or an approximate sampling distribution, we can usually find a really good estimate of whatever the true parameter was. Okay, so with this in mind, we want certain types of statistics for this scenario, okay? So an unbiased estimator is something that we really want, okay? An unbiased estimator is a statistic that when we use it to estimate the parameter, has the mean of its sampling distribution is equal to the true parameter of the population, okay? So I'm going to write that down for you. Okay, so an unbiased estimator is a statistic that we use to estimate the parameter such that the mean of the sampling distribution is equal to the true value of the parameter being estimated. Okay, I would hope that the why is this useful can be, it's kind of obvious, right? If we can get an approximate sampling distribution and we know that the statistic is an unbiased estimator, then we can really, really close to accurately find the true value of the parameter. Because, we can find statistics super easy, right? We can take samples and we can find the mean or the standard deviation of the sample, but we very rarely can find the true population values, the parameters. So this is a really, really, really good way of estimating the true parameter. Okay, so then the last thing we're going to look at, as far as definitions are concerned, is we're going to look at variability and how sample size affects that. Okay, so basically when we take a sample, we have a couple options that could, show up. One is we have a sample that's, really accurate and all of your values in the sample are really close to the true mean, right? So we're accurate and there's not much variability. That's the ideal situation, but a lot of times samples are not so perfectly accurate. So we have 4 different scenarios that could come up. Now the first one, right, if we're looking at a target, this is a great kind of just, visual, right? If this is our target, right, and that's the true value of the parameter, right, perhaps we took a sample and all of the values are in one certain area, right? They're all really close to each other, but they're very far away from the true value of the mean, okay? So this is going to be something with low variability, right, because they're all clustered together, but a lot of bias, high bias. So high bias, low variability. Now the next one, if we were looking at, how accurate it is, it's pretty, if you were to find the mean of all of those dots, right, you're pretty close to the actual middle of the target, right? So in this one, you have high variability because all the dots are spread out, but low bias because you're pretty close to the center. Really awful scenario is if you have a lot of bias and a lot of variability, right? Your sample's just way off and it's not going to be useful at all. And then last but not least, you have the ideal situation where your sample is pretty much right on target. It is where you want it to be and you don't have much variability. And so a case like this would be, something that is an unbiased estimator, right, where the results of our samples are pretty close to what we want, which is the true value of the parameter. And something to kind of keep in mind is this actually relates really well to, your characteristics of your distribution, where your center, your spread, and your shape, right? High variability will be a large spread, right? And then your center, right? If your center is close to the true mean, like I said, that's going to be low bias, So this really strongly relates and correlates with distributions. All right, last but not least, we have an example. Okay, this is called the German tank problem, and basically what it refers to, it's really similar to our textbook problem, right, where we had the number of textbooks. That was what we wanted to estimate. We didn't know how many there were, and so we had to come up with a way to kind of estimate the number of textbooks, right? So in this case, right, we're talking about German tanks, and it goes back to World War II when the Allies would capture a bunch of German tanks, and each tank had a serial number on it. And so the Allied forces, wanted to know how many of the German tanks there actually were. Because I think, if you're an army fighting the Germans, that's probably a really useful thing to know. So anyways, basically what they did is they took the serial numbers, sent them to mathematicians, because we're awesome, and and then they asked for an estimate for the total number of German tanks, which you would call n, right? Because that's the true number, right? Remember where this is your parameter, and your true, and then your sample, right, is little n, which is your statistic. So anyways, there is, I have some data on the next page, which you can look at, that basically shows some data that another class who did a similar activity to what we did, they had the teams in the teacher's class came up with 4 different statistics to estimate the number of tanks. Okay. So the first one was called max-min, and basically they just took the maximum plus the minimum. The second one was mean plus 2 standard deviation, right? And it was, how they did that. And so they just took the mean and then they added 2 times the standard deviation. I think that should be an X bar. Twice the mean was the third statistic they used, and they just took the mean multiplied by 2. And then lastly, they took 2 times the median. Okay, so those are the 4 different statistics they looked at. Then the teacher added one more method called the partition. Okay, and so if you look at the results of, so we took n, little n is 4, and each student took 250 random samples of 4 tanks. Okay, and then with every single one of those samples, they put a dot on their dot plot. Okay, so on this page, right, each one of those dots is a sample of 4, right? They took, they had 4 serial numbers, and on this dot plot here, they took max-min, so they took the max plus the min, and they got that particular value, okay? And then they did that again, and again, and again, and again, and again, and they did that 250 times, right? So there should be 250 dots. Each dot is the max plus the min of one single sample. Okay, so we can look at these 4 different statistics, and then also this partition method, which ended up being the one that was used by the mathematicians during the World War, right? And so the question was, which of the 4 statistics proposed by the students, so which of these 4 is the best estimator? Okay, and so basically you want something that has the least variability and the highest accuracy. So you're looking at bias and variability. And keep in mind that the blue line there is the true number of German tanks, okay? So that is what we're looking for. So we're looking for a distribution that has most of its data centered around the blue line, right, and has less variability. So if you look at the shape of each distribution, you can kind of see this one is skewed to the left, which means, right, the mean is actually going to be, this is actually a biased estimator, mean plus 2 standard deviation, okay, because its center is probably going to be about here-ish, right, which is too high. So you're going to tend to overestimate the mean if you use this statistic. Okay, so this one's kind of out. We don't really like that one very much. Okay, and then if we look at the rest of them, max min, twice mean, and 2 median, all of them approximately have a mean right on the blue line. Okay, which is good. That means that there's low bias, right? And those are going to be pretty accurate. Okay, so then we want to look at variability. Which one has the least amount of variability? And the answer is, drumroll please, it's probably your max min, right? Because it looks like here, the chunk of the data is really towards the center. The rest of them really are a little bit more spread out, right? So max min is going to more frequently accurately predict the mean. So the last one, partition, right? This one was not something that the kids came up with in the classroom. This is the one that the mathematicians actually used. And the reason why is because it's unbiased, right? The mean is pretty accurate, it's right about there. And it's skewed to the left, okay? And there's a very low variability, which means most of the results are going to be in the right area. And the other piece is, even though it's skewed to the left, you're going to be more likely to overestimate. But when you're talking about the context, right, in war, it's better to overestimate the number of tanks that the Germans have than underestimate it. Okay, so that was why they used that particular statistic. And voila, that is the end of 7.1 and what a sampling distribution is. All right, have a lovely evening or day or whenever you're listening to this. Okay, bye.